Boa tarde. Eu venho aqui apresentar o professor Alexander Ioffe, do Instituto de Matemática, do Technion, Departamento de Matemática. Ele tem importantes trabalhos na área de controle ótimo, análise não diferenciável, que chama non-smooth analysis, e também teoria de ponto crítico. E tem contribuído também na área de análise variacional, que envolve esses três assuntos. Então, é um prazer ter ele aqui e a gente vai assistir uma palestra dele. It's a pleasure to introduce here Professor Alexander Ioffe, who has many important works in the field of optimal control, non-smooth analysis, and critical point theory, and also in variational analysis, which somehow involve all these three subjects.
Okay, that's fine. Well, thank you very much for the introduction and for correcting this terrible mistake, so I know how to write correctly. And it is really a great pleasure to be here for the first time. Okay. So, I have to begin with explaining what is regularity and what is variational analysis, what it's all about. Well, regularity is an extremely popular word in mathematics, and today already sounded very strongly in the lecture of Professor Schrödinger. So you must be very cautious with this word, and unless you speak to your close colleagues, you have to define it precisely. The regularity I'll be talking about is really different from the regularity that was mentioned in Professor Schrödinger's lecture. Variational analysis, on the other hand, is rather a new area that came to the existence because of the needs of optimization theory. And for many, just this combination of words is practically unknown, so I have to explain very informally the meaning of these two words now. So, regularity. Well, it wouldn't be too wrong to state that the main object of study in analysis is an equation. You can write an equation like this always, where f is certain operator, or mapping, or function, whatever. And when we deal with the equation, we are, of course, interested in the stability of the solutions of this equation with respect to small perturbation of the right-hand side and the mapping, the operator itself. Definitely this kind of stability, it is among the most fundamental properties that we're interested in dealing with equations. Regularity that I'll be talking about is relating to that kind of properties of equations. Well, it's not surprising, actually, that when we study, when we talk about regularity, when we talk about stability of the equations, then in mathematical terms, then we eventually come to some rather fundamental facts of analysis, and we'll see, well, in the brief survey with which I will start my lecture, that it is definitely so. Well, regularity gives, the regularity property I'll be talking about gives all necessary information about this possible stability in terms of the given mapping and certain fixed solutions. So we actually don't need, and this is the very idea of the whole story, we don't need to look for solutions corresponding to variations of the operator or of the right-hand side to decide whether we have this stability or not. That's more or less in a very brief way explanation of what we'll be talking about. Now, variational analysis. As I told, variational analysis was brought to existence by the needs of optimization theory, for which in its most recent developments at the end of the 20th century and so on, for which the traditional frameworks of smooth and convex analysis were just insufficient. Variational analysis works with non-differentiable mappings and even with set-valued mappings, typically, and it would be equally correct to say that the main object of study of variational analysis is the inclusion, where F is a set-valued mapping. That is to say that for any x, we get not a value, not a vector in certain space, but a set of vectors. And of course, the questions about stability for solutions of inclusions like that are equally accurate and equally important. So I will start my talk with an extremely brief survey of some basic ideas and results of classical regularity theory for linear operators and for smooth nonlinear operators. Just to mention some basic results that we'll be having in mind when talking about variational analysis, about set-valued mapping, just to keep this connection with the classical theory in sight, not to lose it. Okay. So let us start with linear operators. The definition is very simple. We have two Banach spaces. We have a linear operator from one space to another, and we call this linear operator regular if the image of this operator is the entire range space. This means that for every y, this equation has at least one solution. The main result, and really one of the most central results of linear function analysis, is Banach-Schauder open mapping theorem, which says that if A is a regular operator, then it is an open operator, which means that the image of the unit ball of the domain space X under this operator is a ball in the range space, is an open set, well, contains an open set in the range space. For us, it will be especially important to give this theorem, which is very often formulated in this way in textbooks, in some quantitative terms. So I will first begin by defining the Banach constant, which is according to the definition, the maximal radius of the ball in Y in the range space contained into the image of the unit ball. It's not a difficult matter to calculate that this Banach constant gets this expression. It's a very simple expression, actually. And if you apply this to operators between finite dimensional spaces, then you can very easily discover that the CA is precisely the minimal singular number of the operator, the minimal singular number of the matrix, which is the square root of the minimal eigenvalue of this operator. So in this case, it is computed very easily. There are two very important consequences of Banach open mapping theorem. One of these is that the Hausdorff distance between the set of two sets of solutions of our equation corresponding to different right-hand side is bounded by this inequality. This means that the sets of solutions are at least as close as the right-hand sides times the reciprocal number to this Banach constant, which means that the smaller this Banach constant, the less stable is our equation, which is a known fact if you think about common knowledges like I forgot the word, I'm sorry. Anyway, so it is a very common, very well known fact in matrix analysis and so on. The other important characteristic, also immediately relating to this stability issue, is the following. So let us look how much we can spend just to kill regularity of the operator. How big should the operator, which being added to our operator A makes it not regular anymore. So, and the remarkable fact is that this distance to non-regularity is again precisely this Banach constant. So this is more or less the frameworks of regularity theory for linear operators. So there is of course, it's a huge and well-developed, beautiful theory, and I would refer to the famous monograph by Kato, which was recently reprinted in the classical series in Springer about perturbations of linear operator. Okay, let's go one more step further and consider classical, also non-smooth mappings. Smooth mappings, I'm sorry, excuse me. So if you have a mapping which is continuously differentiable at a certain point, then we call it regular at x if its derivative, which is a linear mapping from x into y, is a regular operator. Well, for those who ever worked with differential topology and so on, it's of course very well known that this is really a number one property of the mapping that we're interested in. And in particular because of this, the most principal result of nonlinear function analysis, which is implicit in the inverse function theorem. The formulation is maybe a little bit different from traditional, but it really embraces both implicit and inverse function think and contains a number of applications which really describe the situation we get in this case. So suppose we have a mapping from, I stated for finite dimensional spaces, for the reason that for Banach spaces in general this is not true. So we have a mapping which is continuously differentiable. Let's assume that at a given point x we have fx equal to 0 and that f is regular at x bar. Then in this case we can find a diffeomorphism from this product, for product of the kernel of the derivative and Rm range space onto a neighborhood of x bar in Rn with the following two properties. First of all, the 0 is moved into x bar by this mapping, and the composition of f and phi is precisely y for any x. Let's look what this does mean. If we fix y, then we shall see that fxy is the image of the kernel of the operator. And it's a small image of the kernel, and we see that what we get are solutions of our equation, this one, for this fixed y. So we see that the set of solutions of the equation, at least in a small neighborhood of our point, is a smooth manifold. It is a nice set. This is number one, consequence number one of the implicit function theorem. And the second thing, in the same way, we see that the Hausdorff distance between sets of solution corresponding to different right-hand parts, it is controlled by the difference of this, well, the norm of the difference of these right-hand parts times certain constant k. And again, it turns out that if we take smaller distance, then we can take this k minus 1. Well, then we can take this k arbitrarily close to the reciprocal of the Banach constant of the derivative. So we have stability, and we have really a very beautiful structure of the solution, provided this regularity condition holds. Okay. Let us step a little bit further. Maybe I'll return for a second back. And so the question, which we will discuss in the next slide, is the following. So, okay, so we have this regularity condition, but how typical this condition is? Can we hope that regularity holds typically, that it holds often, that it's not an exceptional property? And the answer to this question is given by the Sirt Theorem, proved in 1942, and probably technically the most difficult result of analysis. To formulate this theorem, we have to define what is a critical value of the mapping. So we say y critical value if there exists x such that fx is equal to y and our mapping is not regular at this point x. So otherwise we say that y is a regular value. Well, when we see that value, that y is regular, or if this is an empty set, this means that our equation doesn't have a solution, or that the set of solution is a smooth manifold, again, is very nice, which reacts to changes of y very nicely as well. So the Sirt theorem says that if our mapping is sufficiently smooth, if it is k times differentiable with k greater than the difference between the dimensions of the spaces, then the set of critical values of the mapping has m-dimensional Lebesgue measure 0. This means that critical value is basically an exceptional phenomenon. The typical phenomenon is regularity. So the world is really good, very well organized. It's important to notice for the future that Sirt theorem is very sharp. There are a number of very sophisticated, actually, examples showing that the sharpness of the theorem. Well, the exact situation is approximately the following, that if f belongs to the class Cn minus m1, which means that it has n minus m continuous derivatives, and the derivative of order n minus m is Lipschitz. For this f, the Sirt theorem is still valid. But if we replace this 1 by certain alpha, which is smaller than 1, and consider corresponding so-called Hölder class, then the Sirt theorem already fails to be valid. The examples produced by Norton in particular shows that for that kind of mappings, Sirt theorem may be wrong. So this is the situation what we have, and well, I will not go ahead of the talk. Here I considered finite dimensional setting both in Sirt theorem and an implicit function theorem. And the point is that I mentioned that these theorems are not valid for infinite dimensional space. In infinite dimensional case, we have a slightly weaker result, which is known as Lusterni-Grace theorem. It says that if we have Banach spaces and we have a continuously differentiable mapping there, which is regular at this point, then the restriction of f to a neighborhood of x bar is an open mapping. So this is more or less the basic principle of nonlinear analysis. It's very similar formulation that I gave to that of Banach open mapping theorem. The main principle is that whatever is valid for linear spaces, for linear operators globally, is valid for nonlinear operators locally if derivative has this property. Okay, so I wish to list a few consequences of the theorem. First of them is that still there is a possibility to get an implicit function type result under the additional assumption that kernel of the derivative splits x, which means that x is a direct sum of two spaces, one of which is this one, which is not the case in Banach spaces in general. Without that, we cannot be sure that this set, the set of solution, has a structure of a manifold. But we can nonetheless define the tangent space to this set. It was basically the Lusternik's result of 34. And it turns out that the tangent space, usual definition of the tangent space. And it turns out that the tangent space under the regularity condition is exactly the kernel of the derivative, which is a very natural fact, actually. It's not true without the regularity condition, and all kinds of singularities can appear there. And also we have a stability type result of that sort. So the deviation of x from the set of solution corresponding to certain y is not greater than the distance from this y to the image of f. I could write this in terms of Hausdorff distance as well, but I prefer this form because it is the most popular and in many cases the most convenient in non-smooth regularity theory. And again, if we take small neighborhood, then this k can be taken arbitrarily close to, can be made arbitrarily close to reciprocal of the Banach constant. That much about the smooth theory. And now let us go to variational analysis. Okay, I forgot about the slides. So two very simple applications of this regularity theories. One of them is stability of critical point. If we have a function and we have a critical point of the function, then the regularity of derivative of this function implies that for functions sufficiently close to f in this metric, any such function has a critical point sufficiently close to the given critical point. So it is one of the actually central result of critical point theory, very simply formulated. The other example, more immediately connected to optimization, is the possibility to pass from constraint to unconstrained. Here it has to be fx equal to 0, subject to fx equal to 0. Well, it's the dream of every optimizator to be able to pass from constraint problem to unconstrained problem, to replace constraint by something, to lift constraint to the function. It turns out that it's possible, always possible, when f is regular at the solution. This, by the way, is an extremely convenient approach to deviation, derivation of necessary optimality condition of any order, and so on. It's very easy to check both of them. Now, variation analysis. Okay, as I mentioned, the typical setting of variation analysis, well, I didn't mention that we have complete metric spaces. Metric space is usually complete, and we have a set-valued mapping from one space to another. So in these examples, I just show how naturally set-valued mappings appear in context of optimization, simple optimization problem. And I'll then explain how important it is to look at these mappings in the context of this problem. So I consider three set-valued mapping. The first is, given X, we consider the collection of right-hand sides such that X is a feasible element in the corresponding problem. In the second mapping, I added one more inequality corresponding to the cost function. Otherwise, it's very similar to that. And the third mapping is with every X associated the number of right-hand sides such that X is a solution of the corresponding problem. Okay? So if we look at the inverse mapping, then we'll see that inverse to phi, which I denoted here, is just a feasible set in this problem. That inverse to psi is just a set of solutions in that problem. It turns out that regularity, which I still have to define, but the regularity of this set-valued mapping at a certain point precisely corresponds to the stability of the feasible set with respect to variations of the right-hand sides. That regularity of this mapping precisely corresponds to the stability of the solution mapping with respect to the variations of the right-hand side. And not regularity, the absence of regularity of this mapping, is a necessary condition for optimality of the problem. So we see that regularity or non-regularity really carries a lot of information about the problem itself. Okay, let's continue. And now I wish to give the main definition. Well, we have set-valued mapping, so we don't have derivatives. With which we defined regularity in the classical situation. So here, variation analysis have chosen, well, so to say, phenomenological definition. We define regularity just by that property which is established as a result of the Banach open mapping theorem or the Stirling-Graves theorem. So let's do the following. First of all, we define so-called functional modulus of surjection of f at a certain point. We see that this is just an upper bound of, well, the maximum radius of the balls which belong to the f image of the ball of radius lambda. And then we do the following. We take lower limit of this functional modulus of surjection divided by lambda, well, elasticity is sort of that, when x, y, and lambda goes to x bar, y bar, and 0. Well, again, the absence of continuous differentiability or linearity, which by itself already gives certain connection between the behavior of the mapping and the near point. The absence of this connection forces us to study x, y in a neighborhood of this x bar, y bar, and then to consider what is the worst possible behavior. Okay, so we shall say that f is regular near x bar, y bar, if this modulus of surjection is positive. The other important characteristic is what is called modulus of metric regularity of f near this point. It is denoted this way, reg f. And this is, by definition, lower bound of those cases. You remember that inequality that we had a few slides before. So it is a lower bound of k such that this inequality holds for all xy of a neighborhood of x bar y bar. And the remarkable fact, not very difficult actually, is that there is such a connection between modulus of surjection and modulus of metric regularity, which is absolutely unconditional. It is always valid for all kind of spaces, all kind of mappings, and so on. It is really surprising that in the classical theory, this observation was not made. Usually, the usual statement was that regularity implies that kind of inequality of which I mentioned. But the opposite fact somehow was ignored, typically. Okay. For two classes of mappings, it's very easy to compute this modulus of surjection. If mapping is continuously Fréchet differentiable, then it turns out that this modulus of surjection is precisely Banach constant of the derivative. So we return back to the situation we had in the classical nonlinear case in this case. It's also possible to do for it is also possible to do for the set-valued mappings which have closed and convex graph, which means that the graph of the set-valued mapping is something like this. It's a convex set, and this mapping with every x associates those sections. It turns out that the formula can be written. First of all, it's very easy to check when that kind of mapping, this mapping is regular, for which y bar. Which y bar is a regular value in the sense of the previous definition of this mapping f. It turns out that it simply must belong to the interior of the image of the mapping. So to the interior of the set to which the mapping, to the projection of the graph onto the range space, if you wish. No, that's okay. Thank you. If you compare this with the definition that we have, with this definition, then you see the difference. Here we have xy going to x bar y bar, and here we have already x bar y bar fixed. So it is really a substantial simplification, and this is really a computable thing. Sometimes not very easily, but nonetheless. So for these two cases, we can get from the definition the complete information about that. Otherwise, computation of this surjection modulus is maybe a pretty tough stuff, and we'll talk about this a little bit later. But the main purpose, as I mentioned in the beginning, is perturbation of the mapping, perturbation of the right-hand side, and so on, what happens with the set of solutions, and so on. So here the approach of variational analysis is the following. So we consider a norm space of perturbations, which are single-valued mappings from x and to y, and we consider additive perturbation. That's to say we have a set-valued mapping f and add to it this single-valued mapping, which means that the value of this mapping f plus p, of course, is fx plus px. Fx is a set and px is a vector, so we know what does this mean. We just move a set by that. So, and we define what is called pay radius regularity of f. And this is the infimum of the norm of p such that f plus p is not regular near this point. sort of the distance to non-regularity, similar to what we have. The two cases are of the main interest. The one is when this P is the set of linear mappings. In this case, we just speak about radius of regularity of F. And the other case is when P is the space of germs of Lipschitz mapping at certain point, satisfying also this equation. In this case, as a norm, we have just Lipschitz constant of the mapping at this point. So we have in this case what is called Lipschitz radius of the mapping. And the perturbation theory for set-varied mappings in variational analysis, at least to the point it is developed now, it contains the following four main theorems. So the first theorem says that if we have a single-varied continuous mapping, continuous on its domain, of course, and if P belongs to this set of Lipschitz perturbation, space of Lipschitz perturbation, then the surjection modulus of this sum is not smaller than the difference of the surjection modulus and the norm of this P. Again, we see that it's very similar to what we have in the linear and nonlinear classical case. This theorem was actually proved in 1980 by Milutin, and for quite a long it was the only result, which is very powerful. And but then, within the last few years, we just found out a number of new facts. These are them. So, first of all, for the same f as here, we have this equality always. So the surjection modulus of f, or it's better to say that Lipschitz radius of f is precisely the surjection modulus of f. Again, the same situation. You remember that in the linear case, the distance to non-regularity was Banach constant. And here we have the same story. Moreover, if both x and y are finite-dimensional Banach spaces, then, with closed graphs, yeah, and f is set-valued, then we have this equality as well, that the linear radius of regularity of f is also equal to this surjection modulus. And again, we know that this result is essentially finite dimensional, and that in infinite dimensional we can find a sufficiently good mapping which has even some differentiability properties, but for which this radius of regularity is strictly greater than surjection modulus of f. Lots of things are still we don't know. For example, what will happen if f is not single-valued but set-valued mapping? Whether this is true or not clear. We don't know. We don't know how to compute this radius in infinite dimensional space, even for single-valued mappings. It's still unknown. So many problems remain unsolved. A few words about proofs. There are two principal approaches to this proof, as written here. The first was originally developed in the classical theory, and Banach, Lusterni, Graves, all of them used certain modifications of the classical Newton method to get the results that I mentioned there. Moreover, further modification of Newton methods were used also in non-smooth situation as well, in particular in the mentioned result, in the proof of the mentioned result by Milutin. However, I know already about one situation more complicated than considered here, is connected with some constraint regularity and so on, for which, so there were a number of attempts to get the proof using Newton methods and so on, and all of them failed. There's another approach based on variational principle of echelon. This is something which I believe may be the greatest achievements of variational analysis, and really which gives an extremely powerful weapon to work in metric spaces. This is the statement of this principle of echelon. Well, it is the result that now already very well known, of course, and very widely used. I just stated it because just it is really so important in variation analysis that practically no development is imaginable without using echelon's principle in one or another incapacity. Well, actually, if the point is that this variational principle of echelon, it is equivalent to completeness. So if you know that in a metric space we have echelon's principle, then we can be sure that the space is complete. Therefore, any fact of analysis and complete metric spaces should be obtained from variational principle of echelon. Sometimes it's easy, sometimes it's not, of course, and impractical, but as a matter of principle, it is really a very important information. And it is really very convenient for use. Now, how to compute those moduli that we defined? Of course, if you remember that this phenomenological definition that basically requires to know solutions of this inclusion, which we really don't know it, we cannot obtain in principle. So we have to use somehow the information that we have in hands, like mapping, like point, given point, and so on and so on and so on. It turns out that it's possible to do, although I just made this change, not only I here, because the technique involved in this, in the developments of these computational procedures is sufficiently complicated, and I would prefer not to explain it too deeply, I would say. So I just gave just one result using the so-called slope of the Giorgio Marino and Toscas, which was introduced for quite a different purpose in 1980. They were looking for a sort of a steep descent procedures for non-differentiable functions, and defined that, and they were trying to prove the existence of that kind of trajectories. It turns out later that this slope is precisely the instrument that allows to give us the possibility to compute this rejection modulus. So this is the definition of the slope, and again there are few cases where it's very easy to compute it. So if you have local minimum, then slope is 0. If f is differentiable, then the slope is precisely the norm of the derivative. And if f is convex, then the slope is the distance from 0 to subdifferential of the convex function. I hope you'll forgive me if I will not define subdifferential of a convex function here, but this is already a sort of a classical object that can be found in...
Domain of f?
Pardon?
What is the domain of f? The domain of small f?
What about the domain? What you ask specifically?
What is the domain?
Certain domain.
Certain domain. What?
It could be anything. So f is function. We usually consider here function which is, well,
We are talking about metric spaces. You are talking about metric spaces.
No. F is an extended real valued function.
Defined in a metric space.
Defined in metric space. Yeah, that's right. But this may be a linear space. This may be a Banach space. If f, of course, if I write that if f is differentiable, then I, of course, assume that it is defined on a Banach space, definitely, on a manifold. Of course, that's. I just take it for granted that if we say about differentiability or about convexity, then we assume that the domain has corresponding properties, of course. That's why I did not understand your question in the beginning. But in connection with your question, I would like to tell something that in variation analysis, we usually consider functions that assume values minus infinity and infinity as well, so-called extended real-valued functions. This allows us to always to think of a function as defined on the entire space. Okay? That's it. Okay, let's continue. This is a technical definition. I would not fix it and discuss it too closely. Just pay attention that this definition is in terms of this slope as well. So there are two simple examples of metric spaces which are locally coherent, which do have this property. It's Riemannian manifold and the smooth manifold in the Banach space with the induced metric, including Banach space itself. So it turns out that if is single-valued continuous on its domain, then we have this inequality. So we consider the lower limit of the slopes of the distances from y to f, where we consider this distance as a function of x. And the only requirement is that y should not be equal to fx. And moreover, we have equality here if the space has this property. A similar result, not similar, but result in similar terms, formulated in similar terms, can be stated also for set-valued mapping, but the statement is rather heavy, and I did not. And I omitted it. There is another instrument of computing, of calculating this modular. It's using so-called non-smooth subdifferentials. I just want to mention that definitions would require really of these subdifferentials would require some work, although using this subdifferential in the practical calculation sometimes it's easier than using those slopes. But anyway, so non-smoothness is a very hard property and we have to work hard to cope with that. Okay. And now we come to the same question that we asked when we spoke about Sirt theorem in the smooth setting. So how typical is regularity for non-smooth mappings? So we have to remember that Sirt theorem is a very sharp result, as I mentioned. So even for differentiable mapping, we have to be very cautious when looking at the level of the degree of differentiability of the function. So probably we should not hope that there are very non-smooth mappings for which this regularity would be a typical property. So the question is how to find a reasonable class of non-smooth mappings, reasonable in the sense that it should, well, typically or more often appear in applications and so on, for which we could hope to get the Sirt type theorem. It turns out that it's possible to answer positively to this question. Well, the first question is, of course, how we should define critical value. Of course, the theory that I already presented gives a possibility to answer this question. We say that y is critical value if there is x such that y belongs to fx and the surjection constant of f at this point is 0. Again, it is a natural adjustment, natural extension of the classical definition of the critical value. And now I wish to describe the classes of maps, of set-valued maps, for which the extension of Sirt theorem is possible. The principal point here is the definition of stratification of the set. and actually Whitney stratification. Well, in fact, we don't need all definition of Whitney stratification. We need only this property A, which says that if we... Okay, let me show the examples. And it would be pretty clear from the examples what we're talking about. So consider, for example, the function like this, the graph of the function. Of course, at 0, we define it as 0. Okay, so we can see that the graph of this function is something like this. Okay? We can break this graph into 3 pieces. One piece is all this curvy line, not including this point. The other piece is this part of this curvy line. And the third piece is this point 0. Right? So look what will happen. If we approach to this point 0 along this curve and look at the tangent spaces to this curve, then it's quite clear that as a result, we get the entire space at the tangent, at the limit of those tangent spaces, right? And here, the tangent space to this point is 0. So we do have that this 0 belongs to the limit, okay? On the other hand, if we consider something like that, set like, well, spiral, but what's that? Let's consider spiral like this, approaching to 0. We also can break it into nice pieces. Those lines, those corner points, and also the limiting point at the end. Okay? But here we do not have this property A because we don't have local finiteness of the stratification. So it turns out that if the graph of F it meets such kind of stratification, CK stratification with K greater than n minus m, this means that it should consist of pieces which are sufficiently smooth, but they could meet arbitrarily. Then the set of critical values has m-dimensional measure 0. So we do have the same property as in the Sirt theorem. The problem is that how to check, how to verify that the set has that kind of stratification. It is not an easy thing, actually. And I would like to just to finish my talk with a brief description of a class of functions, class of sets, class of maps, very broad, finite dimensional, of course. Well, I didn't tell that there is certain infinite dimensional extension of Sirt theorem due to Smale. And I didn't mention it here because, first of all, it applies to not to all kind of differentiable maps, but to Fredholm maps. So it would require, again, a number of definitions and so on. And also it works only for separable spaces, and there are a number of restrictions. But anyway, so the same story is here. We can state something like that for certain class of infinite dimensional situations as well, but it would be it would involve a lot of additional necessity to introduce a lot of additional information and so on. So from this point, I'm sitting in infinite dimensional space, in Euclidean spaces only. And I will start with introducing the sets which are known as semi-algebraic sets and mappings. It's a very important class of sets, widely used in algebraic geometry in particular, and so on. So these sets are obtained in the following way. Let's consider unions and finite unions and intersections of sets like this, where f is a polynomial of n variables or smaller, and so on. So this is the definition of some algebraic set. Set obtained as a result of finite union or finite intersection of sets like that is some algebraic sets. And two simple examples of the sets. You can consider graphs of polynomial splines like this, the semi-algebraic set. Or we can consider solutions of that kind of linear matrix inequalities, which plays an extremely important role in modern optimization theory. Now, it is also a semi-algebraic set because, well, this inequality means that certain determinants are positive or negative, and so on and so on and so on. The most remarkable properties of the set is this Tarski-Zeidenberg theorem, which says that the projection of some algebraic set onto space of smaller dimension is a semi-algebraic set. It's really a great theorem, and it allows to do a lot of things which I just list a little bit later. In fact, well, semi-algebraic sets, well, we say a function is, or mapping is a semi-algebraic if its graph is a semi-algebraic set. Such mappings of functions need not be continuous. They need not be bounded. They could be need not be differentiable, of course. But they do have, of course, some specific property that distinguishes them from sets and functions of other sort. But I want to just briefly mention a broader class of sets and mappings which eventually have the similar type of properties as some algebraic set. This is a new and really very beautiful theory developed within model theory and algebraic geometry, and now becoming increasingly popular in analysis, in non-smooth analysis in particular. So this is a concept of O-minimal structure. I will not go too far in the definition. Just I would like to... O-minimal structure is a sequence of sets. In every dimension we have a collection of sets, and these sets have certain properties. We have the possibility to go from y dimension up to high dimensions through Cartesian products, or we have the possibility to go down through projections like that. And also we have this property that says that the elements of S1, the sets in one-dimensional space, are just finite unions of points in open intervals. That's it. So you make projections, and eventually we can come to something like that, not a difference. Then you will have the collection of set, what is called O-minimal structure. I will give reference at the end, so I would be very brief here, just explaining that there is certain kind of good sets and good mappings. So we say that a subset is definable if it belongs to the structure in corresponding dimension. The set is called tame if its intersection with bounded definable sets is definable set. And these are definitions of definable and tame functions and definable and tame mappings. Well, tame, it is an English word which means domesticated, nicely behaving, not wild, pathology-free, and so on. There are some properties of definable and tame sets and functions. They allow topological operations. They allow all algebraic operations. They allow all functional operations like image, pre-image, and so on. The composition of definable mappings is a definable mapping. We can do this type of things with definable function and get definable function as well. And the derivative of a definable mapping is a definable mapping as well. So you see that practically everything that we can do in analysis will leave us within this class of definable sets. And again, and definable function. And again, they need not to be continuous, they need not to be differentiable, but they have certain restrictions introduced by these properties, in particular, that I mentioned. And it turns out that every definable set does admit CK stratification satisfying this Whitney property R for any K. So if necessary, we can add more pieces, can take a finer stratification and eventually get stratification of any level of smoothness. Therefore, we can formulate Sirt Theorem for definable maps in the following very beautiful way. That if we have a set-valued mapping which is definable, then the set of critical values of F is a definable set, not just having Lebesgue measure 0, but having dimension smaller than m. The class of definable sets, of course, is restricted, but it turns out, and it was discovered in optimization theory in particular during last several years, that in typical optimization problem, the functions that we meet, the functions that we work with, they do belong to that kind of classes, one or another, or minimal structures and so on. And this is precisely the class for which the regularity theory for invariation analysis can be, well, and hopefully will be completed up to the same level of perfection as it has in the classical theory. Now I wish to give some references to complete. These are classical works of Banach, Graves, this book of Kata that I mentioned, and Lusternik, where the basis of classical regularity theory were introduced. These are some monograph and survey articles that two very recent monographs, one completely finite dimensional and one in which infinite dimensional, but certain class of infinite dimensional spaces considered so-called Asplund spaces. And these are references relating to definable sets and mappings for anybody who could be interested in. That is it. Thank you very much. The reference for what?
For the last theorem you mentioned.
It will appear in an article in Proceedings next year, I think. It is.
What is the reference?
That's what I'm talking to. The reference is my paper, which we'll call Sirt's Theorem for mappings with stratifiable graphs. It will appear in Proceedings, probably in the beginning of the next year.
You said something about the measure theory for definable maps and how that could be used to change your domain of Rn, your theory.
I'm sorry, I have not understood the question.
Has measure theory been extended to definable maps, definable sets, so that one could formulate more Sirt's theorem in terms of definable maps instead of Rn and Rn?
But it is, the statement is better than in terms of measure. Well, the final statement is saying that this is a set of dimensions smaller than m. It definitely has measure 0. You see, so this is a better statement thanks to definability. Well, you can look, there are some things, there are some works about measure theory for definable stuff. You can look in the book by Just van der Dries, and there is some, not much actually. This is a very fast developing theory, so it is, there are not many results that I know at least, but there are some. But the fact is that the definable set whose measure is 0 must have smaller dimension. That's much better than just measure 0.
Thanks again, Professor Ioffe.